Hi guys. How you guys doing today? How's everybody doing?
Good, how are you?
So just some administrative stuff before we it. We don't forget your homework is due tonight. That'll be homework for 4.2 and 4.3. Let's do by midnight tonight. And we have a quiz that's going to open up at 3 o'clock today. Or our class gets done, our quiz will open up. That'll be on chapter 4.2 and 4.3. I know I had said originally 4.3 part 1, but it's like 4.3 part 2 was just more examples. So it's all, kind of similar to that. And then today, what's going to happen is we're going to do 4.4. 4.4 is very short, really concise. There's stuff in there that we can cover fairly quickly. And then, oh, sorry. And then we're going to go through like one lecture example for that. And I should be done with that fairly shortly. And then I'd like to open up the class for questions on homework problems for 4.2 and 4.3. So if you guys don't have any questions on homework, you can leave after I'm done talking about chapter 4.4. Or if you want to listen to what other people have to ask about, or if you have questions yourself, then you can stay till later and then we can talk about it. So that's what's coming down the pipeline for it. And then I was talking to some students in office hours today about how do we know how to calculate Z for our error calculations. What do we choose for that? And actually in the process of talking to them in office hours, we came up with a nice summary for all of those. So before we jump into homework questions, I'll do a quick summary for those different. How do we know where to choose this max of f of n plus 1 of z? How do we know what to do for that? So we'll have a whole discussion about that too. All right, so with that said, let's go ahead and jump into chapter 4.4. And remember, I'm going to cover this, fairly quickly, and then we'll have time to talk about 4.2 and 4.3, which I'm sure is where all of your questions are. Okay, so chapter 4.4. There's a lot in here that's kind of redundant with stuff that we've covered before, but this is called functions as power series. So up until this point, we've been using power series. Remember, power series doesn't mean, oh, it has a lot of power. It means it's got a power, an exponential, something, a polynomial, a variable raised to a power. And a series, because it's typically an infinite series. Okay, this thing's going to go off. We have an infinite number of terms there. So before, we've been representing or approximating functions with power series. That was our Taylor and Maclaurin power series in particular. And we now we're going to say that there are certain functions that are actually equal to their Maclaurin. Okay, so let's just go through some stuff. Some of it we'll be reviewing. I'm going to try to go through the review parts more quickly, and then we'll focus on the new things. So let's think about. So we've got functions can be approximated. This is what we've been doing. Approximated by an nth order, which is our highest degree term. Our highest degree term is n, an nth order Taylor or Maclaurin, depending on, oops, I'm running out of space, Maclaurin polynomial. Remember, Taylor and Maclaurin are the same, except that a equals 0 and a equals some number other than 0. Okay, and then importantly, right, there's actually two important things, but the higher the degree, higher the order, our polynomial, the better the approximation. Okay, higher the degree, The higher the better our approximation. But importantly, there are some types of functions, we're going to talk about those today, some types of functions that are actually equal to their Maclaurin. Are actually, let's see, equal to their power series, their infinite power series. And I'll write Maclaurin in particular. Okay, so this is like an infinite polynomial. So some functions are actually equal to their infinite polynomial, okay? And so when we talk about these functions being equal to their power series, we're going to talk about convergence. So we're going to talk about how this infinite series, will converge, to a function. Remember we talked about convergence with the improper integrals, right? So we've got, it's a limit, right? So as we approach this infinity, where is this thing going to? Well, in this case, we're going to take the limit of our power series and it's going to converge right on top of our function. So it's going to become right our function. So let's just remember, remember what is our power series? So power series is basically, it's a sum, right? So I'm going to write it, or like our polynomial. We use our dummy variable n, we use k, you know, whatever. It goes up to infinity. We have our coefficient c sub n, x minus a to the n. Now some books will write this as an a and this as a c for where it's centered. You know, I'm trying to keep it consistent with what we've done before. So c sub 0 plus c1 x minus a to the first power, c2 x minus a squared, so on and so forth. C sub n x minus a to the nth power plus dot dot dot. Look, it goes on forever, right? Even past infinity. So n goes whatever some number, and then it just keeps on going until we run out of time, right? So c is our coefficient. Remember this, we used in the Taylor and the Maclaurin series, we used the function and its derivatives and its behavior at our center point in order to derive our coefficients to make this a meaningful power series that was equal to a polynomial that was related to that function. And then a is where it's centered, where our polynomial is centered. And that's going to be specific to the problem that you're working on. Okay. So let's talk about convergence of a power series. Like, what do we mean? I'll let you guys finish writing that. And then we'll talk about convergence of a power series. Okay. So convergence of a power series, this is our definition. Okay, so let's talk about what that means. So if we've got a couple pieces. So I've got my power series. X naught, all we're saying with X naught is, where do we want to look? I want to make this power series centered at A, and I want to look at values of X. We've talked about this as 0.01, 0.001, or 1.1 or whatever, right? I mean, this is some specific value that we want to evaluate our function at, and this is where we've centered it. So now I'm going to say the limit as n goes to infinity, dfn, x naught of a. So kind of like what we did with our improper integrals, where I replaced the infinity with a limit. So now we're going to evaluate our power series as a limit. As we approach out to an infinite number of terms, where is this function, this polynomial going? And this is equal to the limit as n goes to infinity. Let's enumerate out what our Taylor, our power series, is going to look like. So f of a plus f prime of a, x naught minus a, plus f double prime plus Fn factorial. Oops, sorry, there, because we're going out to infinity, so there's no dot dot dot. Okay. Oops, sorry. It's like I knocked over my camera. All right. There. Okay, so all we did was we said we're taking the limit of our power series. Okay, so let's talk about what that means with our limit, right? So if the limit exists, then the power series converges, right? And it converges, we're going to talk about what it's going to converge to. Otherwise, like if our limit doesn't exist, otherwise, this diverges. Okay, it doesn't converge to a particular function. So let's elaborate on this. So if the limit exists, if our infinite series converges, okay, to our function, right? If it converges to our function, then the limit as n goes to infinity of our error, the error goes to 0, right? So if this power series converges to a function, the error goes to 0, right? It makes sense, right? Because if we say that our power series equals our function, there's no difference between the power series and the function. The error is just going to go right to 0. So this is what we're thinking of right here, okay? So let's I'll write that in English here down. So the error is 0 if the power series converges to the function. And it's going to converge to the function if our limit exists. Okay, I'll let you finish writing that, and then we'll remind you about a couple things about limits to keep in mind. Okay, so I'll scroll up a little bit here. Okay, so just a reminder, some notes about limits. Make sure you remember the conditions under which a limit are gonna not exist, right? We've got 3 conditions that we can think of off the top of our head. Let's say x is some fixed number. Okay, so the first thing you want to keep in mind that if the absolute value of x is less than 1, so it's a fraction basically, right? Then the limit as n goes to infinity of x to the n is equal to 0. Think about it like this. If this is equal to 1/2, right? So x is equal to, 1/2. So 1/2 is less than 1. So 1/2 squared, 1/2 cubed, 1/2 to the 100th. These numbers are getting smaller and smaller and smaller and smaller. So as n gets bigger, this thing goes to 0. These are just some things to remind you so that when you're processing your limits on these series, and then as we get into chapter 5, it'll make sense and you won't have to kind of think it through. Okay, so then our second thing to think about, regardless of the size of our absolute value of n, if we say our limit as n goes to infinity, x to the nth power all over n factorial is equal to 0. And what this means is that the factorial gets big as a number, gets big much faster than x to the n. Okay, so, and this is like, so you don't have to do L'Hopital's rule with a factorial, So basically, x squared over 2 factorial, x to the 100 is pretty big, but 100 factorial is much bigger. Okay, x to the 1000, that's a pretty big number, but 1000 factorial is even bigger. So this thing goes to 0 because n factorial gets much bigger, goes to infinity, gets to infinity before x to the n gets to infinity. So it helps you kind of think about how you're going to process these limits, because we're going to be processing this kind of stuff, especially in chapter 5. We're going to be dealing with these kinds of processes as we go. Okay, so this is sort of like a Cliff Notes version of how you want to think about limits. Okay. All right, so let's talk. So I'm going to write down some of the functions that, I'll put a star here, some functions that are equal to their Maclaurin. Series. And these are theorems. I think we actually put a whole list on one of our lecture example pages. I forget, we did it on like the back page. It wasn't exactly like an example, but it was a list that was important. But we'll just put it here again. So e to the x as an infinite series, as a Maclaurin infinite series is going to be, we're going to start off, we'll go k equals 0. So we're using a different variable k. It doesn't matter if you use k or n or whatever. X to the k factorial. So in summation form, right? And that's going to look like 1 plus x squared, x cubed, x to the 4th, and so on and so forth. So e to the x is equal to its Maclaurin. Now remember, this goes out like to infinity. So we do partial sums, okay? But if we use this function, if I take the limit of this function, it converges to e to the x. So sine of x, right, a summation, k equals 0 minus 1 to the k, x to the 2k plus 1, odd numbers. So on and so forth. And our cosine of x is equal to okay, so on and so forth for cosine. Okay. ln of, oh, sorry, this is ln of 1 plus x. This is equal to there's no factorial here. Oops. Sorry, squared 2. Oops, sorry, that's a negative. It's to the 4th, and so on and so forth. This is going to converge for x being between -1 and 1. It converges. So this Maclaurin series will converge to ln of 1 plus x when x is between -1 and 1, and it's going to diverge outside of that. So just as an idea, when x is equal to 1, we're going to get the ln of 2, which comes out to what we call an alternating harmonic series. You're going to learn about all of this in chapter 5. We're going to do that next, but just to kind of preview of coming attraction. The harmonic series is 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Alternating means it alternates in sign, positive, negative, positive, negative, positive, negative. We're going to be dealing with harmonic series are pretty important in engineering. So just to kind of throw that out there right now. Binomial. This one I think you may have a homework problem on, a couple homework problems. So I'm focusing on this. Our lecture example focuses on this too. So where p equals a real number, I've got, this is going to converge for -1. X is between 1 and -1, it converges. It's going to converge to 1 plus x to the p. The Maclaurin for this is equal to, I'll enumerate it. I didn't do the summation form for it, sorry. 1 plus px right? All I'm doing is, this is the Maclaurin for this right here. So my my first, you know, when I evaluated at x equals 0 or a equals 0, right? So my first term is 1. When I take the derivative, I get p, right? And then I evaluate it x equals 0, so it just becomes 1. So p times x. My second derivative, I've had to subtract, you know, p minus 1 from here, so it's going to go p times p minus 1, right? So that's where all this comes from. This is just from taking the derivatives of this and deriving my Maclaurin. Okay, so now there's I used to cover this problem. This is my lecture examples for this here. We used to do problems like this more. We don't cover this kind of problem so much anymore, but I'm gonna cover it for you guys because I think there's a homework problem like it, and sometimes it pops up, but we tend not to test on it anymore. But let's go ahead and do this so the homework isn't, you know, quite so bizarre. Can you go back to their page for a bit? Sure. How's that? And we're going to use the binomial, Maclaurin for the binomial in order to answer this question here. Okay. All right, so use the binomial theorem to approximate radical 3.8. This is kind of like a thought process, how we get there. So we need to get this in the form of 1 plus x to the p power. Okay, so that's kind of like my goal. So I'm going to be thinking first off that radical 3.8 is equal to 3.8 to the p, 3.8 to the 1/2. So then p equals 1/2, right? Is kind of how I'm thinking about it. So I need to think about now, how do I get this into the form of 1 plus x, right? And so I can assign values to x, and I've already got my value of p assigned. So let's multiply. I'm going to think, let's see, so 3.8. So if I represent 3.8, the next perfect square up from 3.8 is 4. 4 minus 0.2 is equal to 3.8. Well, if I plug this in, 4 minus 0.2, that's not the same thing as 1 plus x. So I'm going to just kind of keep in mind that this is 4 minus 0.2 gives me 3.8. So this is like one of my goals. So what I'll do is I'll say I'm going to multiply 3.8 by 4 over 4. So 4 over 4 is equal to 1, right? This is still radical 3.8, but I've multiplied it by 1. 4 over 4 is equal to 1. So now what I can do is I can say I've got a radical 4 times, or I'm going to factor this out, radical 4 times 3.8 over 4. Okay, I'll kind of put this back into radical form so you can kind of think about it that way. Now let's substitute 3.8 with 4 minus 0.2. Don't forget this radical 4 that we've got from here. This radical 4 is the same thing as that radical 4. So this becomes 4 minus 0.2 all over 4. Okay. Now I can distribute the 4 to both terms, and I'm going to convert this 4 into a 2. So this is going to go 4 over 4 minus 0.2 over 4. Okay. And now I've got, this is 2 radical 1 minus 0.2 divided by 4, 0.05. So this becomes 2, 1 plus a negative 0.05 to the 1/2. So what I have is p equals 1/2, my x equals minus 0.05. So now I can put it into my 1 plus x to the p format. So my first order Maclaurin for the binomial series is going to look like, we did it out before, 1 plus p times x. So knowing that p equals 1/2 and x equals minus 0.05, I'm going to plug it in 1 plus 1/2 times minus 0.05. And then what I get as an approximation for 3.8 is 1, oh, I'm sorry, and I goofed because there was a 2. I forgot my own 2. This 2 here is a multiplier that we factored out. So when I do this, don't forget you're multiplying by that 2. So this becomes 1.95. Okay, if I do a third order Maclaurin, I'm going to write down what we had before. That's equal to, remember we've got the third order Maclaurin is 1 plus px plus p times p minus 1, 2 factorial, x squared plus p minus 1, p minus 2, 3 factorial, x cubed. Right, so this is going to be equal to 2 times, and I'm going to plug in for p and for x. So this goes 1 plus 1/2 minus 0.05 plus 1/2, 1/2 minus 1, 2 factorial minus 0.05 squared plus, you can fill out this part here, 1/2, 1/2 minus 1, 1/2 minus 2, 3 factorial minus 0.05 cubed. You don't forget to multiply it by 2 at the end. And when we're done, I'm going to get this, I got 1.94936. Okay, when I do this on my calculator, right, radical 3.8, my floating point calculator goes 1.9493587. So it's not bad, right? It kind of bombs out right there, which is, we did the third order. So 1, 2, 3, 4. So right, so it's not bad, you know, for only a third order. Anyway, it's simple. That's it for 4.4. We don't really talk about this so much, but you will need the binomial series, I think, for a couple homework problems, and probably specifically for one that looks just like this, where you have to estimate it. Okay, so now what I'm going to do is, let's see, I want to answer some homework questions, but I also want to talk about how do I choose f of z depending on the different types of functions that we have. So let me cover that that idea first really quick, and then we'll talk about homework problems. I'll let you guys ask me questions on 4.2 and 4.3. How's that? All right, so let me so let's think about, we covered, this is our discussion of f of z, right? And it's a common question and everybody asks, and it's a really good question. Like, what is f of z? How do I know what to choose for z? Let's see if I can get this. No, it really didn't cooperate. Okay, so how do I know what to choose for f of z? So the functions that we covered in class, right, were of 3 different classes of functions. We had our trig, our sine of x, cosine of x. We have our exponential functions. Mostly we do base e, so e to the x. And we have our logarithmic functions, mostly natural log, okay? So we're going to go through one at a time. We're going to talk about f of z. How do we choose that? So what happens is in our, let's do this. I don't want to tell you too much all at once because it'll be overwhelming. Give me a sec. Okay, so as you know, when we talk about our f of z, we're looking at our max value, because our whole goal is to find max of our n plus first derivative evaluated, some imaginary approximate, not imaginary, but some approximate number z, right? It's not even like a real hard and fast number. So the first thing I have to do is I have to look at my derivatives. All of these ideas about f of z come down to what are your derivatives doing, right? On a trig function, my derivatives basically are sine or cosine. And there's like a plus or minus that's happening. And then on this function here, I don't have any multiplier here. I don't have like a 3x or an x over 2 like in our homework. So I'm not accumulating any numbers out front, right? Like with my chain rule would give to me. So my amplitude for my sine or cosine is going to stay equal to 1. So now based on my derivatives, right, I can take a look at and I can say, well, geez, let me summarize. My derivatives are positive or negative. They're either sine or they're cosine, right? Depending on which derivative, which n I choose. So I always do f of n first. And then from there, I'll just increase n by 1. I'll say f of n plus 1. right? And it's not changing anything here. But I think we, one of your homework problems has like a 1/2 that's accumulating. So you've got a 1/2 to the nth power that's accumulating each time. So it didn't really change anything here. So now when I go to figure out what's my max f of n plus 1, I'm here, I'm going to look at f of n plus 1 of x, but it's really, when we talk about z, we're going to talk about z in just a minute, but I'm going to look at first x. So that's basically max of my sine or max of my cosine. The plus or minus goes away with the absolute value, right? And anyway, I'm looking at my sine or cosine functions oscillate, right? And how come when I go to look at my z value, we say our z value is between a and x. So it's like if I'm looking at a Maclaurin, I'm like right around 0. Or maybe I'm looking at something like pi over 2 or something like that, or pi or whatever. And then, you know, I'm going to be looking, how come I don't find an exact value or look at within that window? And it's beyond the point for trig functions, and we look for a maximum value. The whole point about this is the maximum part. I need the number that's going to represent a maximum possible number of my derivative functions. My derivative functions are sine or cosine. These things oscillate, right? And their max value is represented by their amplitude. Okay, so in this case, our amplitude is equal to 1. Okay, so my max value is the amplitude, which is just equal to 1. So the whole max, fn plus 1 of z, is equal to 1. I think on your homework, when you have sine of x over 2, you're accumulating these multiples of 1/2. So it becomes like 1/2 to the n plus 1, and that's my amplitude, right? So depending on what derivative I'm on, like that n, right, is going to tell me it's 1/2 to the 4, 1/2 to the 8, 1/2, whatever we're talking about. So that max is my amplitude. Okay, that's my trig function. I'm looking at amplitudes. Okay, so trig functions we deal with, you know, you have to look at all your derivatives. The derivatives are going to depend on the nature of the function itself. Okay, but the sine and cosine, I'm not so focused necessarily on specifically where's z, but really what's my function doing. It's, you know, like it just bounces between plus or minus amplitude values. All right, so let's think about our e to the x functions, right? So e to the x now, okay, when I go to take, this is another class of functions, exponential functions, when we take their derivatives, the function is within its derivative, right? Even if I had a chain rule, like I think there's an example in our homework that has a 3x here. So I'm accumulating multiples of 3 out front, say for example, from my chain rule, but I still have the function. No matter what I do, I've got 3 e to the 3x. I've got, you know, 3 squared e to the 3x, 3 cubed e to the 3x, or in this case, it's just plain old e to the x. I've got the function itself within the derivative. That's true for all of our exponential functions. The function itself is within our derivative. So now I'm going to come up with my nth derivative is just simply, for this case, e to the x, which is equal to my function, right? Exponential functions. I go up to my n plus first. I always find it easier to generalize to n plus first once I've come up with an nth derivative. It's because all I do is I add 1 to n. So now I need to look at my max of f of n plus 1 of z. Now, with exponential functions, because our function itself exists within the derivative, I have to ask myself what value is going to maximize my derivative. Now, because my function is within the derivative, right, if I plug in my z is between a and x, this is usually where we're looking. We want to look at values of x equal to something, right? If I look and I say, okay, this value will maximize my my derivative here, the problem is that that's the function that we're evaluating. If I plug in that number, that's the function I'm looking for. That's the solution I'm looking for. It won't give me an upper bound. It'll give me an exact answer for my error. I don't want an exact answer. I want an upper bound. I want my error to be just slightly above the exact answer, so I can say the error is tight with the function, the approximation, okay, but we haven't gone so crazy, okay? So now I have to ask myself, right, instead of e to the x, where z equals x, I have to choose some logical value of z that's just slightly greater than what x would be. So I get an upper bound on the error. That's where you make this judgment call. And there's going to be, you know, you guys are all going to have hopefully different answers, right, than each other. And then you may have my choice, you may have something slightly different, but that's why you have to show your logic. So possible answers for this are, right, so say for example, if we want to look at x equals 0.1, right, so if I go e to the 0.1, that's giving me my function because my derivatives have my function in them. So I can't go my exact function. So e to the 0.1 is less than e to the 0.5. Okay, so I'll choose e to the 0.5 as my max. Or possibly I could say e to the 0.1, right? Let's do it out. So I would say e to the 0.1 is equal to 1.1, right? So 1.1, okay, is less than 2. So e to the 0.1 is less than 2. So 0.2 becomes my maximum value. It's not my z value, it's my maximum value. If I did z equals 2, e to the 2 is way bigger than I need. I just need something that gives me an upper bound. So my max fn plus 1 of z equals 2. And this number goes into my error equation. That's for exponentials. ln, right, our last discussion on ln, right, think about what happens when we do, oops, natural log. When I take the derivative of the natural log, I get 1 over x squared, 1 over x cubed. There's like positive and negative, and I've got numbers accumulating. There's a factorial in there. I'm not going to think about that just for the moment because I need to, we're thinking conceptually more here. So I've got 1 over x, 1 over x squared, 1 over x cubed, x to the 4th, right? So basically I'm looking at 1 over plus or minus 1 over x to the n times some number. It's the factorial. I'm not going to worry about it right now. So this is what I'm looking at for my nth derivative, okay? 1 over x to the n is a decreasing function, okay? So like we had a homework problem, which we can talk about, where, where our z value goes between 0.9 and 1.1, right? And so, but the problem is I have to look, this is z, right? But I'm going to plug in, this becomes, when I go to evaluate this for my f of n plus 1, this becomes 1 over z to the n when we go to evaluate it. So I need to rewrite this inequality to recognize, right? Because my n plus first derivative of z is 1 over z to the n plus 1, right? So 1 over z. So I have to rewrite this. I have to take the reciprocal of this whole inequality so that it reflects the nature of my derivatives, 1 over. So if I take 1 over z, then I have to flip 0.9 and 1.1. Well, 1 over 0.9 is bigger than 1 over 1.1, so the bounds change, right? So to maximize 1 over z, I choose z equals 0.9. Now, how come I can choose a real value for z along my interval, but I couldn't for e to the x and sine? Well, it's the nature of the derivatives. So the nature of my derivatives do not contain the natural log. So I can choose an exact value for ln, right? My e to the x had, the function is in the derivative, and then, you know, the function's in here too, but these functions, the trig functions, are special because they oscillate, right? So we're looking at z.9s. This becomes, right? So it's this is our factorial 0.9 raised to the n plus 1. That becomes our max. Okay, so 3 classes of functions and 3 things that we need to think about when we approach this stuff. I know this is, I'm going kind of quick. This was something that I covered in office hours with a couple students. They thought it was very helpful, so I thought I would share it with you guys. All right, enough said about that. Questions that you guys have for homework, I am happy to go over. You guys can speak it or you can write it in the chat. I'll do them in order that we see them.
Could we go over problem 1 from homework 4.3?
Sure.
Actually, like point C.
Especially point C. Yeah. Give me a second on that one. So, all right. So this one says so this is 4.3 question 1, right? So this is like our sine, but we're accumulating 1/2 values. So this is 4.3 question 1, and we'll do A, B, and C because they there's important parts in all of this stuff. So we've got f of x equals the sine of x over 2. And now they gave us a bunch of other information. And then we want a reasonable upper bound. So T3 F0 what is the error, oops, our third order error, sorry, that's a 3. So this tells us it's Maclaurin, right, because our A equals 0. All right, so let's come up with our table. We're going to need our table anyway to come up with our, to be able to come up with our formula for this stuff. So our derivatives. And I'll do this, but I'm going to go quick on it because we don't really need this part because they're just asking about the error. So our f of x, right, our f of 0 equals 0. When I take the derivative of my chain rule, it means I've got a 1/2 that accumulates. Now I've got a negative, I've got a 1/2 from before and a 1/2 that's new. Right, I'm gonna write it out like this because I'm gonna need that for convincing myself of a formula. Actually, I'm gonna stop this part here because I don't think I need this because I'm not coming up with an actual equation. So let's just do our derivatives. Right, so I'm gonna get minus, whoops, 1/2 times 1/2 times 1/2, that's a 2. Cosine x over 2. And they said to go to third order, which means I need n plus 1, so I need the fourth. So this is going to be plus, it's going to be 1/2. I'm going to have 4 of them. So it's 1/2 to the 4th sine x over 2. Okay. So now let's just generalize. So my nth derivative. So my first derivative, I had 1. I've got a plus or minus, right? Positive, positive, negative, negative. So I have, there's a 1/2 that keeps accumulating. So my first derivative, I had 1. Second derivative, I had 2. Third derivative, I have 3. So it seems to be to the nth, and it's sine of x over 2 or cosine of x over 2. Okay. So now I need to be thinking about my max absolute value fn plus 1 of z and what that's going to be. So my n plus first derivative is going to be just n plus 1, 1/2 to the n plus 1. But let's take a look first at our sine and cosine, right? So my my sine function looks like this. Well, I'm not drawing it very well. And my cosine function is the same thing. That's just shifted, right? So depending on what derivative I'm at, right, my amplitude is 1/2 to the n, right? This is positive 1/2 to the n, this is negative 1/2 to the n, right? Depending. So really, regardless of where my z is, where I'm focused or where I'm looking at, along my whole function, I'm maxing out at 1/2 to the n. So, but we want the 1/2 to the n plus 1 because it's the n plus first derivative. So I'm going to look at that. So n plus first, right? This is my max, okay, of this function along that interval. So my error, my third order error, right, is my, I'm going to go like this. It's going to be, it's Maclaurin, so it's going to be x to the n plus 1 all over n plus 1 factorial, and then this max fn plus 1 of z there. So let's fill in the blanks. So they told us at the beginning, absolute value of x was less than 0.1. So I want the upper bound. So I'm going to plug in my highest value. My n equals 3. So this becomes 3 plus 1. 3 plus 1 factorial. This is a plus. Max, we already did this part. This is 1/2 to the 3 plus 1. Right, so this is 0.1 to the 4 factorial, 1/2 to the 4. This is a number. What did I get? I get 2.604 times 10 to the minus 7. So this is a reasonable upper bound on the error. Okay. Now for part B, they say they want us to fix the error and solve for n. So we're going to fix the error. So I'm going to, everything else is the same, right? And then we're going to say n equals what when error is, the upper bound is going to be, what did they say, 0.0030, 1, 2, 3, 1. Okay, so I'm gonna set all this whole thing here less than that. So I'm going to go like this. I'm going to go 0.1, but I'm going to go n plus 1 all over n plus 1 factorial 1/2 to the, because I don't know what n is, but I want it to be all less than 0, 0, 0, 1. And then solve for n. Well, this is trial and error. Don't try to actually solve for n, you know, because it's going to blow up. Just try trial and error, but use what you have here. So my n here, my n was 3, and I got a really small error. So I'm going to try n equals 2. I can go smaller. So n equals 2, I'm going to plug it in. So I'm going to go 0.1 to the 3, 3 factorial, 1/2 to the 3, and that gives me 0.1234 That's still actually smaller, so I can actually try n equals 1 and see what we get. 0.1 squared, 2 factorial, 1/2 squared, and that gives me 0.00125. So this one's too big. This one, it seems small, but it's like n equals 1 is too big, n equals 2 fits, so we're going to do that. Okay. So that's part B. Yeah, so why is this equal to that? So you're asking where do we get the f of z from for the sine, and that comes from our amplitude. And we were accumulating multiples of 1/2 on every derivative. So it becomes 1/2 to the n plus 1 because every derivative has a 1/2 on it. Okay, so let's do part C. So part C says basically how we're going to handle part C is we're fixing the error. So the error, we're fixing the order and the error. So the we want the third order error to be less than 0.001. Sorry, there's 3 zeros, 0, 0, 0, 1. And we want n equals 3. And we need to solve for x. But x, this is equal to our delta. So this is like, what's that little window that we're working around? And because we had such a really tiny error here, this delta is going to be bigger than the 0.1 that we worked with before. So let's go back up to, this is why we spent so much time coming up with this formula here, because we're going to use it again down here. So my my third order error, whoops, sorry, I should write this as an E. Error is going to be x to the 4th, 4 factorial, 1/2 to the 4, and I want this to be less than or equal to 0.0001. They gave me this. So I'm going to solve for x. This is my delta. So when I solve for x, I multiply everything. I'm going to get x to the 4th less than 4 factorial times 2 to the 4th times 0.0001. I'm going to take the 4th root of everything, and I get x was equal to, I want absolute value of x, which is my delta, to be less than or equal to 0.4426. So I can actually widen my range of values that I'm looking at. The derivatives don't disappear. We're looking at the max value. The max value on our sine or cosine function is the amplitude, so they don't really disappear. Remember, always, it's not f of n plus 1, it's the maximum of f of n plus 1 of z. So the maximum is always the amplitude. All right, let's see. So
Thank you.
you're welcome. 4.3 number 13 is the next one somebody asked about. So let me just read it really quick. So 4.3 number 13, it said to find an upper bound on the error where x is within plus or minus of the delta that they give. So this is our sine of x function again, and the delta they gave is 0.3. So let's take a look. Okay. Okay, so this is 4.3 number 13. There. Okay, so we're looking for En of x, and this is Maclaurin. So our function equals sine of x, and our delta equals 0.3. So basically what this means is our absolute value of x is less than or equal to 0.3. So I would say x is between 0.3 minus 0.3. Okay, so basically, although it's this value that I'm going to worry about. So what's going to happen is, remember our derivatives. I'm going to go quicker here. Sine of x. Okay, and I'm not evaluating them because they didn't ask me to come up with the Maclaurin polynomial for it. They just said, what's the error? So this, when I go my f of n plus first derivative, okay, at z, I'm looking at, this is plus or minus sine of x or plus or minus cosine of x. The amplitude is equal to 1. So this is my maximum. Is equal to 1. Okay, because that's the amplitude of my sine or cosine functions. Okay, so x is less than or equal to 3. So now when I go to think about my upper bound on my error, right, I've got how we write it out is we say absolute value of x, n plus 1 factorial, and I've got max f of n plus 1 of z. So let's fill in the blanks for what we have. So this becomes, right, this part they gave us, this becomes 0.3 to the n plus 1 factorial, and it will be multiplied by 1, but we don't need it. This is a formula. We would come up with a formula for the upper bound on the error, given that our delta is 0.3. I'm going to hold off on the example, our lecture examples, because we have the solutions up for that. But let me look at 4.3, number 5, part A. So 4.3, number 5. 5 is ln of x. So ln of x is, we did the ln of x when we did, yeah, I guess, so these are similar, right? So this is example 4 from 4.3. So this is like what we did before. So this is our ln of x, right? So we're centering this at a equals 1, okay? So I've got ln of x, I'm deriving my ln of x function. So I'm coming up with my f of n plus 1 derivative. So let's think about this one. So this is 4.3, number 5. So we've got f of x equals ln of x, and we're told x minus 1 is less than 0.1. And we're looking for the error of our third order when a equals 1. So this is a Taylor, right? So when we do this and we go our derivatives, right? This is just like our derivative. So see lecture examples 4.3, number 4 for derivatives and coefficients. So we actually came up with our Taylor for this one, which we're not asked to come up with the Taylor on here. We're asked just to come up with the error. So let's skip right to the end when we talk about our nth derivative. So when I look at all of my derivatives, right, I'm accumulating an n minus 1 factorial. My sixth derivative has 5 factorial, right, and so on and so forth. So we've got a factorial thing that's happening. So my nth derivative, I got a minus 1 to the nth power. I have an n minus 1 factorial, and that's all over x to the n. That's just looking at my derivatives and looking at the pattern that the derivatives show me, right? So we did this yesterday when we came up with our derivatives for ln of x, right? So this is, my coefficients are an n minus 1 factorial. So my fourth derivative has 3 factorial. Fifth derivative has 4 factorial. Sixth derivative has 5 factorial. Whoops. So that's where I'm getting this from, n minus 1 factorial. I don't worry so much about the negative 1 to the nth power because I'm gonna take the absolute value of it. X over n, right? That comes from our derivatives as well. So I'm looking at my derivatives. I've got 1 over x squared, 1 over x cubed, 1 over x to the fourth, so on and so forth. So this is 1 over x to the n. Now, when I want to do f of n plus 1, let's go this at z. So we haven't done the max yet. We're just going to substitute z in for x. So I'm going to increase by 1 everywhere I see an n. So minus 1 to the n plus 1. N minus 1 plus 1 just becomes n factorial over, oops, sorry, this is a z. Z to the n plus 1. Okay. So that's just my f of n plus 1 of z derivative. Okay, now I need to think about how I'm going to calculate the max. Okay, now this problem in particular says we're dealing with we're going to deal with let's see, what did we say? We said x minus 1 less than or equal to 0.1. Okay, this is what was given to us at the beginning. So I'm going to rewrite this to be I'm going to get rid of the absolute value. So that's between negative 0.1 and positive 0.1. I'm going to add 1 to both sides. This is going to be 0.9 and 1.1. Okay, so my x is between 0.9. All that means is, remember our ln function, right? We're focusing, we're looking, this is my x-axis, this is my y. My ln function comes up at x equals 1. And I'm going to look a really narrow window right around that. So I'm looking at numbers between 0.9 and 1.1. Okay, so that's what I need to think about. So now, if I go to substitute, when I go to do the f of z, I'm going to substitute and I'm going to say 0.9 is less than z, which is less than 1.1. Not bad, except that, look what we're dealing with here. When I deal with my f of n plus 1 of z, I have, I'll take the absolute value of it so I can get rid of the negative. So I've got n factorial all over z to the n plus 1. I've got 1 over z happening. I need to be able to compare apples to apples. So I've got, this is a z. Z goes between 0.9 and 1.1. But before I can evaluate what number of z is going to maximize my derivative, I need to do something to say, well, this is 1 over z. So I'm going to convert this into a 1 over z also, so I can think about that. Well, 1 over 1.1 is smaller than 1 over 0.9. So 0.9 will maximize our value. So I'm going to plug in 0.9 for z here. So this is going to become n factorial over 0.9 to the n plus 1. That's my max. Let's write this. Max n plus 1 of z is right here. Okay, that's this bit. Okay, so now we put this together for our error calculation. So my error, and what they tell us, a third order error, is going to look like x minus 1 to the n plus 1 all over n plus 1 factorial. We're going to substitute an n for a minute, and I'm going to plug in this. This is going to become n factorial 0.9 to the n plus 1. Okay, so now let's put things together. So I've got the factorials. So I've got n factorial all over n plus 1 factorial. I want you guys to do this out and convince yourself. N factorial is n times n minus 1 times n minus 2. N plus 1 factorial is n plus 1 times n minus 1, so on and so forth. So this just becomes 1 over n plus 1 times x minus 1 to the n plus 1 times 1 over 0.9 to the n plus 1. This bit here they gave me at the beginning. They told me this was equal to 0.1. So I'm going to plug that in. So I'm going to go, and my n equals 3. So this becomes 1 over 4 times 0.1 to the 4 times 1 over 0.9 to the 4. And I just multiply that out on my calculator. And I got my third order error was going to be less than or equal to 0.1234381. Okay. 4.3 part A. Part B and C. 5B and C. Okay, so while we're here, let's go ahead and do B and C. So B and C are like what we did before, where we have to, B is just trial and error on my n. So let's go ahead and do that. So this is, let's do this. And then I'll let you guys look at that. See if we can scroll up. All right. So this is 4.35 part B. So this is find the smallest value for n that's going to make this. So remember we had before, let's plug it in. So I had 0.1 to the n plus 1 all over n plus 1 times 1 over 0.9 to the n plus 1, right? So I need to try, I'm going to try n equals 2 and then just see, because this is a pretty small error, because they wanted our error to be less than 0.1231. Okay, so I'm going to plug that in. So I'm going to go 0.1 to the 3 all over 3 times 0.9 to the 3. And I got, what did I get for that? 0.00045. Well, they wanted it to be less than 0.001. I got 0.0001. I got 0.0004. So this is too high. So I'll keep it at n equals 3. Okay, but I got this formula from all the work I did in part A. Okay, and then part C is, part C is, there's a lot of algebra in part C. I'm going to skip all the algebra, but I'll set it up for you. So 5C, x minus 1 equals delta. And so we need to find delta, right? And so we're fixing n equals 3 and the error to be less than 0.0001. Okay, so we need to find our delta. So I'm going to set this all up again. So I'm going to go, instead of 0.1, I have to go x minus 1 to the n plus 1 all over n plus 1 times 1 all over, and we have to be careful. There's a whole calculation about delta and z again. So this is, I'm going to go back to z to the n plus 1. So this is a tricky part for this. So when we did it before, we said x minus 1 was, 0.1, but now I'm going to go, so now this becomes delta, oops, sorry, that's not an 8, that's a delta plus 1, x minus 1, less than or equal to, let's see, this should be negative minus delta, delta plus 1. So this is 1 minus delta, and this is 1 plus delta, right? X minus 1 is, we got rid of that. Okay, because we added 1 to both sides. So x is between that and that. So now if I plug in z for this, right, but we're dealing with 1 over z, so this becomes, right, this is going to maximize it, 1 minus delta, right, because this is a bigger number, so it makes this 1 over a smaller number. So this maximizes. So this one's a little trickier than just plugging it in and solving. So I need to set up this whole thing again. So this is going to go, all right, let's do this out. This thing is going to become delta. So delta, so n equals 3. So this is going to become delta to the 4th all over 4th times 1 over 1 minus delta to the 4th. We want this to be less than 0.0001. And there's just lots of algebra which you can work out and then do. And then I found delta equal, delta was going to be less than or equal to 0.12389. It's a pretty wide delta, and we could get away with that because our error was pretty tight on part A. Okay, let you guys keep running. I'll get out my 4.2. Rachel, do you have a preference? Why don't we just choose one, 16 or 20 on 4.2? I'll let you choose. 20 is 20.
What were you gonna say? Sorry.
20 is straightforward. 20 is just here, I'll just show you 20 really quick. So 20 is like, we did this Mclaren in class by substitution. We got this as our Mclaren. It's our lowest degree term, contributes the most to it. So n equals 3 on number 20.
Okay, thank you.
Yeah, and then 16. Okay, I'll scroll this up a little bit here. 16. This is now 4.2. 4.2 number 16. I'll do that out. 16. We've got h of x equals ln of x, and we're asked to find a second order. Looks like a Taylor evaluate at x equals 0.9. So my 0th, I'm deriving these now, ln of x, which gives ln of 1, which is 0. So I'm doing my derivatives, my whole table again. Okay, so it's just second order, so I only have to go up to my second derivative. So I'm going to put this in. Let's write out x first. So this is going to look like 0 plus. This is going to be 1 times where I'm centered. My coefficient is negative. Squared all over 2. It'll be 2 factorial, but it's just 2. So this is our polynomial. And now I'm going to plug in 0.9. So I'm going to go 0.9 minus 1 minus 0.9 minus 1 squared all over 2. And I'm going to get minus 0.105. Part B says, what's the difference between that and our calculator value? So this is going to be the absolute value of 0.9 minus, right? And I'm just plugging these in for my calculator. And I'm looking at a magnitude because it's an error. Minus 0.105360557 minus a minus 0.105 gives me 3.60515 times 10 to the minus 4. Okay. All right, guys. Kind of a blitzkrieg problem set, but phew. Okay. All right. Hey, you guys have a great day. Have a good weekend. And I'll see you guys all on Monday. Okay, don't forget homework's due tonight, and the quiz will open up at 3 o'clock today.
Thank you.
Bye, guys.
Thank you.
Take it
Bye.
easy.
Thank you.
Take care.